Welcome. In this session, we will distinguish between two critical performance metrics in AI infrastructure, bandwidth and throughput. We will examine how they differ in a GPU-centric environment and the technologies required to maximize both. Start by clarifying our terms. Bandwidth is the potential capacity of your hardware. For example, an NVIDIA Connect X7 adapter allows a peak of 400 gigabits per second. However, you rarely get the full 400. Throughput is what you actually achieve after accounting for overhead like packet headers and network friction. Think of bandwidth as the width of a highway and throughput as the number of cars actually arriving at the destination per hour. In networking, we focus relentlessly on closing the gap between the two. We want our throughput to be as close to the wire speed bandwidth as possible because any gap represents wasted GPU cycles where the processor is waiting for data rather than computing. This visual demonstrates the reduction from potential to reality. We start on the left with our theoretical bandwidth, the raw capacity of the cables and switches. As data moves right, it encounters friction protocol headers, latency, and congestion which act as filters. The result on the right is actual throughput. Our goal in AI networking is to minimize that middle friction layer to maximize the output. GPU-centric architecture, the bandwidth numbers are staggering. Inside a server like the GB200 NVL72, GPUs communicate via NVLink at 8 terabytes per second. This is over 14 times faster than the standard PCIe Gen 5 bus found in traditional servers. We call this scale-up bandwidth. It essentially turns multiple GPUs into one giant accelerator. We also need scale-out bandwidth to connect different servers. Here we use 400 or 800 gigabit InfiniBand or Ethernet. The critical takeaway is that AI workloads are tightly coupled. If one GPU is starved for data because throughput drops, the entire distributed training job pauses. High throughput is not just about speed, it is about keeping these massive processors fed to maintain synchronization. This diagram contrasts the internal data paths. The thick green arrow represents NVLink, offering a massive 8 terabytes per second pipe directly between GPUs. Compare that to the thinner lines connecting to the CPU via PCIe Gen 5, which only offer about 64 gigabytes per second. This illustrates why modern AI keeps traffic on the GPU to GPU NVLink rails whenever possible to maximize throughput. To achieve high throughput for AI, we must bypass bottlenecks. We use RDMA remote direct memory access to let GPUs read and write directly to the network, completely skipping the CPU and OS kernel. This is essential because AI generates elephant flows, massive sustained bursts of data that would overwhelm a standard CPU. However, these massive flows are risky. If two collide on a switch, they fill buffers instantly, causing packet drops. A dropped packet is catastrophic for throughput because resending it stalls the calculation. This is why we use advanced congestion control, found in SpectrumX and InfiniBand, to throttle traffic intelligently before drops occur, ensuring the tail latency the worst-case packet delay remains low. Here we see the RDMA flow optimized by congestion control. GPU sends a massive burst of data directly to the switch, bypassing the CPU. The switch detects potential congestion and, instead of dropping packets, signals GPU to slightly adjust its rate. This ensures the data stream to GPU B remains continuous and lossless, maintaining high effective throughput. Finally, software libraries like NCCL maximize throughput by choosing the best path like rings or trees for data to travel, but we can go further within network computing, specifically Sharp. In a typical all-reduce operation, GPUs exchange data, do math, and exchange again. Sharp moves that math into the network switch itself. The switch receives data from multiple GPUs, adds it up, and sends back only the result. Less data traverses the network. Sharp effectively doubles the bandwidth performance for these operations. This, combined with rail-optimized topologies where GPUs of the same rank share a switch, ensures we squeeze every bit of throughput out of the physical hardware. This diagram compares standard operations versus Sharp. On the left, data must travel to a GPU to be computed and then sent back, consuming bandwidth both ways. On the right, with Sharp, switch ALU arithmetic logic unit accepts inputs from GPU A and B, computes the result instantly in the network, and distributes it. This reduces traffic volume, thereby increasing effective throughput.